Welcome back. So far we have used novice-level graphics and some really bad humor to try to help you understand some of the aspects of the first law of thermodynamics. If you remember nothing else to this point, hopefully you remember in minus out equals change. Most recently we talked about the three types of energy that can change: internal, kinetic, and potential. We also had a discussion about microscopic versus macroscopic energies, and we finished with a look at the first law for closed systems.
That's wrong. My book says Q equals W plus U.
Well, it's not what I would call wrong. Truth is, you're going to find some variations in the way the first law is presented from one textbook to another. But most engineering students who have already passed physics and integral calculus will notice the equivalence.
Maybe you should brush up on your algebra.
Why? No one ever uses that stuff.
When introducing the first law to students, I prefer to use this form. Now, to get here from the raw differential form of the first law, we have to employ some assumptions and simplifications. Most of these assumptions we can worry about later, but one is essential. This equation is for closed systems. Have you noticed that I tend to repeat things over and over again? Closed system. That's to give you the crazy idea that those words are important. Closed system. Closed system. Now that we have planted that idea in your head, let's look at these two words. Let's start with the word system. What does that mean?
Oh, that's what I use to win when I gamble.
Not the type of system I had in mind.
A piece of equipment, like your steam engine.
That could be a system.
What about something small, like a water molecule?
The truth is, anything could be a system. Even Izzy, the queen of mischief, could be considered a system. Yeah, she looks all sweet and innocent until you try to move her, and then she bites you. What were we talking about again?
Systems, sir.
Oh, right. Okay. A system can be as small or as large as needed. Simply put, a system is a region in space to be analyzed.
That's a really broad definition.
I agree, but it is accurate. Here's a more practical definition. A system is anything we can draw a dotted line around. The dotted line represents what we call the boundary. Everything inside the dotted line is our system, and everything else is what we call the surroundings.
A dotted line, sir? That seems really informal for a technical definition.
Well, it probably is. But let's face it, these videos are by no means formal, so I think we're okay. Rather than worrying about being formal, it's more important that we have a simple way to define a system. Clearly defining a system boundary is crucial for keeping track of a conserved quantity. Drawing a dotted line around our system may seem like a silly, trivial step, but it makes our analysis straightforward. Hooray for something simple. Now let's consider the word closed. What does a closed system represent?
Something sealed.
No, that's a type of energy, right?
The correct answer: a closed system doesn't let mass in or out.
Right. It's sealed. Mass is not allowed to cross the system boundary. However, energy can cross the boundary in the form of heat or work. Okay, wait. You said the equation in my book is wrong, and the book's definition of a system is wrong. So I should just not read my book and listen to you, right? No. Honestly, that is not my point at all. If you are taking a thermodynamics course, you should be reading your text, solving homework problems, working example problems, going to class, assuming you're not taking the course online, going to discussion sections or drill sessions, and attending office hours, TA hours, or any other resources your school may provide. Thermodynamics is non-trivial for many people. You should be utilizing a combination of resources to help you get the point across. It is my hope that these videos can provide an entertaining way to augment the resources you should already be using. Now, I also hope that we have some people in the audience who are not thermo students. Some of you may be watching these videos for other reasons like learning or just simply entertainment. Just for you guys, here's another picture of Izzy and her slave, Lilly. Yeah, you think they're all cute and cuddly now. Just wait until the little one actually figures out how to use the internet. You saw her earlier, watching me work on my computer, trying to figure out how it all works. Soon, she'll figure out all my passwords and get on my computer when I'm not looking. Then, we're all doomed. She'll distract you with her cuteness, every last one of you. Then she'll change all your passwords. Finally, she'll shut down the entire global economy, one person at a time. What were we talking about again?
Things that a successful thermo student should do.
Right. And here's what you really need to know. Your success in a thermo course, as well as many other engineering courses, will be based on your ability to solve problems. Let's look at a fairly generic problem-solving strategy and apply it to this example. First, we need to define the problem. Then, we need to organize all of the relevant information. Next, identify the applicable concepts, laws, and relationships, and find a reasonable solution. If you can master this process of solving problems while learning basic thermodynamics, you will be well on your way to becoming a successful engineer.
Why can't we just memorize the material and take tests? That's what I've always done.
Well, that's because we're training you to be an engineer and not a source of memorized knowledge. Essentially, an engineer will apply existing knowledge to formulate a solution to a practical problem. Engineering students in a thermodynamics course should have two goals: develop problem-solving skills and learn the basics of thermodynamics. So, our future episodes will continue to expand your knowledge of thermo and re-emphasize problem-solving skills. Hey, thanks for watching. If you liked it, give us a thumbs up, subscribe, and don't forget to follow us on Facebook. Stay tuned, there will be more videos to come.